So I'm going to set the context of this presentation up front, because when I've done this before, I've had a number of questions that are related to the context. This is a limited context. I'm talking specifically about fog node security, not about general network or orchestration security or how the system as a whole works, but what, from the point of view of the fog node, what is needed in terms of security. And the point about horizontals and verticals, there is, we spent a lot of time, Rodolfo spent an exceedingly large amount of time looking at a number of different verticals and use cases across those verticals. And one of the things we did after that, I have a slide in another deck, I haven't got it here, but we looked at the horizontals, the striped, those verticals. What did we need to do across all of those verticals in order to provide an infrastructure that was useful and could be shared and leveraged? And again, this is about technology, not products. So there's no Cisco products either expressed or implied in this particular presentation. And the other thing, this is all about enabling multi-tenant and consolidation models. So many of the speakers already have talked about those models. Fog is specifically about that. It's not about a single user dedicated device. Though those devices are required in the network, that's not what we're talking about when we're talking about fog in general. So I'm going to talk about three fairly broad subjects. I'm going to talk about the challenge of creating a fog infrastructure, go through some security basics. I'm going to define some security terms, go through those rather quickly because I'm going to use them in the subsequent slides. And one of the things that's happened when I did this presentation before is I'd use those terms and get stuck in the middle trying to explain the term and how it related to other security terms. So I'm going to try and do that up front and get that out of the way. And then I'm going to talk about fog node platform security. So the security challenge for IoT, and especially for fog, is depending on whose numbers you take. This is one that's supposedly based on a Cisco projection. 50 billion connected devices by 2020. So the big problem is how do you create a secure infrastructure of that scale? So it's not only the node, but if the guy next to you is insecure, then all was for naught as you transfer data. As intelligence, local data storage, analysis, and other compute moves towards the edge, many devices are going to be located in unsecure places. I think the other speakers have talked to that, things on telephone poles, things by the street, things by the road. These fog nodes, these nodes that are going to do analytics, data collection, connect to other higher level fog nodes, they're going to be in very insecure and public places. So the challenge there is how do you create a node that handles data in a secure manner? And not all nodes are going to need all of the features. So just as Carl was talking about up in the data center, there's several things they just ignore because they assume a secure building, a secure entry, a secure cage. Not every security mechanism will need to be implemented in every node. And the last bullet is there's no such thing as absolute security. Security is a relative thing. There's always people who will find a way around any security mechanism that's invented because they have infinite time and apparently infinite attention. So here was an interesting, or I thought it was interesting anyways, a analysis done by Open Web Application Security Project. I think they did it along with HP. But in any case, they looked at current IoT devices and came up with the top 10 security issues in IoT devices. And not surprisingly, those all apply to fog. And the 4 areas that need to be protected during the slide is the data, the network, the device, and the hardware and software and firmware infrastructure. All of those, once compromised, or any of those once compromised, will compromise or can compromise the entire system. So quickly through some definitions. Security properties, often abbreviated as CIA, not the CIA that we've all known to love, is the cornerstone of security. So confidentiality, integrity, and availability. These will be available in the slide deck, so I'm not going to go into great detail here. And security that's needed by any given platform is defined by the threat model, both those threats that are being considered and those that are not being considered. So as Carlos was talking about with the data center, they've looked at the physical security of the data center and said they don't need to do certain things like encrypting data between machines because they're in a secure environment. So in that case, the threat that's ignored is the man in the middle, somebody tapping the wire and looking at data. Attacks are what's obvious, and instantiation of a threat violates the security properties of the system. And again, no such thing as absolute security. Policy versus mechanism. So security policy specifies who or what can access which resource under which conditions, and the mechanism implements that policy. A trusted resource is responsible for these terms are often used interchangeably, and they're really not. A trusted resource is responsible for maintaining security policies. A trustworthy resource is designed to be secure. And unfortunately, or fortunately, well, mostly unfortunately, you can be trusted and not trustworthy, or you can be trustworthy and not trusted. Just because you're designed to be secure doesn't mean you're trusted in a specific environment. It depends on the environment you're incorporated into. And just because you're trusted doesn't mean that you don't have any security flaws. So TCB is something you'll often see, trusted computing base. It's all of the hardware, software, and firmware and networking components that have to be correct and uncorruptible in order for the security policy not to be violated. Trusted execution environment is a secure area of a process storage that guarantees the code and data that are located there are protected with respect to confidentiality and integrity, the CNI and CIA. So it doesn't cover availability, which is the A. We'll talk about that a little bit more. Access control, you'll often see AAA referred to, authentication, who you are, and authorization, what you're allowed to do. Privacy, which we talked about earlier, is the right to decide how your information is used. It's not the same as confidentiality, which is the responsibility to prevent unauthorized disclosure. So one is identifying data with specific attributes. The other is carrying out the intent of those attributes. And privacy is built on top of other security mechanisms. So finally to the main topic. So this is a single slide that I built the rest of the presentation around. I'm not going to go through it here. I'll go through it at the end, and hopefully I've covered all these points. But this more or less summarizes fog node security. So there are 4 categories of fog node security. Trusted execution environment, which we talked about, data security, network security, and physical security of the node, tamper-proofing, and intrusion detection and amelioration of either of those events. Trust has to be rooted in hardware. It has to be established at power on and sequenced up through hardware bring up. The trusted components of the system has to be verified and eventually get to a trusted boot, which brings up either a hypervisor or bare metal OS. And in that way, you can extend the chain of trust. But if it doesn't start with a hardware root of trust, you don't know what you're extending. There's a hole there. And something could have happened. And in fact, one processor vendor that I know of, they had a firmware implementation of this, and at power on, it was invoked, and they discovered a hole in the firmware where somebody could get in. They had to go back and patch all of their firmware implementations on all of their subsequent processors, and on the processors they could patch. They couldn't fix it on some, however. So trusted execution environment. It's static, it's established in installation and sticks. We'll go back through the picture later and look at this in terms of the picture, but essentially the hardware root of trust and chain of trust extensions defined by the Trusted Computing Group, the hardware starts in a known state, trusted state. There are various implementations of how you extend that trust depending on manufacturers. So with Intel, there's things like TPM and BootGuard and TXT. With ARM, there's TrustZone. With other manufacturers, there's security processor. And I use that term here. When you look at several manufacturers' description of their processors, they often will use the term security processor in two ways. And one of them is very often simply an encryption decryption device. It's not something that helps with the chain of trust. So just because you see that term, don't believe that it's necessarily this. Static root of trust. So a static root of trust, as we talked about a little bit earlier, essentially comes up, manages the hardware bring up, verifies things like the boot block, the BIOS and firmware, option ROMs if there are any, and then transfers control to the bootloader, a trusted bootloader, which it is verified, and then that bootloader invokes either a bare metal OS or hypervisor, which it also verifies, and that again becomes a trusted execution environment. Dynamic root of trust, in the case of a virtualized system with a hypervisor, the individual VMs can then dynamically establish and extend that root of trust up through the VM and potentially the applications in that VM. But they can come and go. You start and stop, so they're not sticky. They're established when the VM is established, and they go away when the VM goes away. That doesn't cause any issues for the static root of trust that was established when the system was booted. The other comment here is about minimizing TCBs. So one of the objectives here of structuring the bring up and the components involved in the bring up and those involved in VMs in such a way that the trusted computing base is minimized so that the target for the attack surface, target for attacks is minimized. That just because you compromised one thing doesn't mean you compromised anything else. Of course, it is hierarchical. If there's a way in around the initial firmware, if there's a way in around the hypervisor, if there's a way in anything lower in the chain, then you can compromise everything up, but you can't compromise down. Some of the other functionality that is available on some processor implementations and in some software implementations are introspective. They're dynamic and they're performed during execution. So just because you've verified something you've loaded and you trust who gave it to you, doesn't mean it doesn't have flaws or isn't infected. All it means is you validated what you got was what you thought you were getting, and you got it from who you thought you were getting it from. So what this does is allow that code to be dynamically checked during execution. Now, one implementation is hardware-based, and it depends on physical page, host physical pages, which means there's a small number, and they have to be essentially pinned. So they have to belong to the hypervisor. So it's useful, but not nearly useful enough. There are other implementations which provide runtime integrity checking using software and hardware. The software is implemented in the hypervisor. The hardware is implemented in the processor and devices, and excuse me, that software is using the hardware on the processor to be able to intercept any changes to areas of memory that shouldn't be changed. So there's front-end tools typically that identify code and static data, no matter where they happen to be in that particular set of applications. And then that's loaded. The software running in the context of the hypervisor then protects those pages and can detect any writes to those pages, and then carries out a policy based on somebody having violated that policy, that particular implementation. There are also techniques like nested guest memory access control, where you can essentially, within the same address space, identify different access to parts of memory as you proceed up the tree, the call tree. Now, obviously, you can't allow anybody up the tree to upgrade their access to memory. You can only downgrade it as you go up. So it's truly a vertical tree. But that allows you to, again, minimize the TCB. And one implementation I've mentioned there is Secure Enclaves, which is available at Intel. There are others. Execution environment. So virtualization is not only a mechanism to allow multiple entities to share the same physical hardware, but it's also a security play because it provides isolation and it provides the ability to configure QoS because you can dedicate specific hardware to specific VMs. It supports a multi-tenancy and consolidation model. So where you have to be able to guarantee in some cases, and we'll look at that in the last slide again, guarantee in some cases specific, and when I use the term QoS, that's sort of equivalent to SLA. What it means is I can guarantee you response, things like response time, things like the availability of certain device access within a time frame, so you don't access a device and get an answer 2 minutes later. I can dedicate that device. I can guarantee you certain attributes of the system within your address space and guarantee that nobody else can upset those attributes. So the other important part of that is in a virtualized system, I can guarantee you that the slice of the physical system that I've configured cannot be affected by slices other executing entities own. I think I probably covered that. Oh, last comment is about containers. They're appropriate in certain cases. There are exceptions. And you have to carefully evaluate what you're trying to get out of implementing a virtual instance. So at the bottom is a quote from a guy who works on Docker, and it says, if you can't read it, reality check. If you run something which by definition needs full control over hardware or kernel resources, and the resources I added because that's what he really meant, the word was left out. Containers are not going to make it secure. Please stop trying to shoot yourself in the foot safely. So you have to, again, it's a trade-off, like any security mechanism. You have to carefully evaluate what attributes you want your execution environment to provide, and then you configure it appropriately. In some cases, it'll be containers. In some cases, it'll be VMs. In other cases, if you look at, again, at presentations about Docker, for example, it'll be your container or containers in a VM to separate it from everybody else because you want certain guarantees. Execution environment. So we talked about this a bit before, I think. Data at rest. So file systems, disks, those kinds of data storage devices. You really need to think about encryption at the file system or object level. Whole disk encryption means that once the disk is mounted by the operating system, that everything will be in the clear as it's transferred to and from the disk. So if there's any shared buffers anywhere in the system, unless all the data is cleared out of those buffers as somebody finishes with it, and even while they're working with it, somebody could potentially be scanning those buffers because those buffers are in shared memory, typically. Everybody has access to them, so they can look at the data in the clear. That's an issue. Typically you want end-to-end encryption, where the data on the device is encrypted, comes in encrypted, the application sees it, decrypts it, works with it, throws it away. And it works with it in its own address space. It doesn't work with it in a shared part of the address space. Memory. So memory encryption there's a number of papers out there on it. It's coming. A number of people are talking about implementing it. It maintains confidentiality by encrypting when the data is evicted from last level cache, and re-encrypting when it's fetched into decrypting when it's fetched into the cache. Of course, the problem here is the penalty. There's a fairly not insignificant penalty on data access from memory. And you have to, of course, have encryption devices attached to the memory subsystem that can encrypt and decrypt at memory speeds. And that's not cheap. Secure debug. One of the things people often forget about is debug. You can't afford to leave any debug open on any of the platforms that you deploy. Of course, you always have to allow for maintenance. And what that means is that has to be protected in such a way that you can remotely authorize an authenticated entity to make use of the debug function. Otherwise, you end up with what we've seen in our industry. Something goes wrong, the customer says, your box is broken, here, take it back. And it costs you hundreds of millions of dollars to deal with the fact that it's not something broke, nobody has a way of identifying it, and so the customer, the easiest way is to swap out the box. That's a very expensive proposition. TRNG, I just mentioned that because cryptography is a big part of protecting the data, and TRNG is required for many cryptography functions on the platform. And it needs to be provided by the platform itself, preferably as part of the ISA, the instruction set architecture. This is a 5-layer cake picture of a converged network security model. And it talks about, we've talked about many of these terms, especially IT and OT. So what we're beginning to see with OT, I think that's been mentioned before, is that there's a convergence between IT devices and OT devices because OT devices are becoming too expensive, require too much to manage, and they're very difficult to extend. You just pile in another box if you want to do something new. That's not a good economic proposition, and it's not a very scalable proposition. If I shut something down in that environment, I take the box out and throw it away. What you really want to do is take the software, put it on the box, run it for however long you need, take the software off if you no longer need it. You've still got the box as a resource. So data in motion, network security. You need encryption at line rate. So obviously it's needed for both data at rest and data in motion, which means your encryption device has to be able to handle whatever rate your incoming, outgoing traffic is and whatever rate your traffic to disk is. Needs to be hardware assisted, at least in some ways, either an encryption SoC device for high bandwidth or for lower bandwidth applications. ISA support may suffice. MACsec, one of the many 802 dot somethings. So MACsec, Cisco has MACsec implemented on almost all their products. The reason is because it ensures that the frame came from where it claims to come from, and that you can't have man-in-the-middle attacks. Nobody can inject traffic, and they can't snoop traffic because it's encrypted end-to-end. The issues with it, however, is now been made optional for TrustSec, and it's not on all PHYs, especially those at the higher bandwidth range. That's may not be a problem for many fog devices. Many of them are not going to need 100 gigabit in a single attach, but it is going to be a problem because it's been made optional. Wireless LAN has implemented the equivalent of MACsec. Although it takes several standards to actually be secure, the first implementation was found to be pretty insecure, and there's the 802.1 AR apparently has fixed that until the next time, I guess. VLANs everywhere. So you want to be able to overlay a secure set of connections on logical connections on the physical network. You want to be able to share the physical network in a secure way. You absolutely need VLAN support in this environment. Remote attestation. Geez, I'm gonna get through these in no time. Last time we did it took an hour. There were questions during it though. Fog node security. Remote attestation ensures unaltered software running on the remote system so that you can ensure yourself that they are what and who they said they were. And it's important for things like controllers, orchestrators, remote services, east-west, north-south partner flows, and for secure software upgrades. Software upgrades would be rather meaningless if anybody could send you an update to your code and get you to apply it. So there's a lot of stuff that has to wrap around that. I'm not going to go into any of those details. Carl has covered some of them, but they're much deeper dive than I'm going to do here today. Remote orchestration. It requires an end-to-end trust relationship. Identity management is important, both on the device agent, so there's going to be an agent that runs down the fog node, and there's going to be something that orchestrates from up in the network, probably a data center. AAA is important here. A secure communication channel, so a VPN or something equivalent. The on-device agent has to be authenticated and authorized to manage remote resources. Authenticated for local resources. The remote agent has to be authenticated and authorized to manage remote resources on this node. Pretty much the last topic here. I'm going to finish early. Intrusion detection and amelioration. Processor SoC devices, boards, chassis level detection. That's typically sensor-based. There's an internal mesh to protect the internal components, typically on the board. There's an external mesh to protect the chassis and I/O devices. Those sensors signal the system, typically firmware running on the device that was initialized when boot up occurred. And voltage and frequency monitors for the same reason. If somebody's tapping something or sending you data or has replaced a part, voltage and frequency variation on that system may well indicate you're the object of an intrusion. Self-resetting parts are also very important when those parts, for example, hold encryption keys and secret data. When the system is reset, those parts should clear everything. And of course, just detecting it isn't very worthwhile. You need to be able to take some policy-based action based on the detection. The policy has to be protected because, for example, you have to be able to allow maintenance to the system. So you may want to be able to change certain policies like debug we talked about earlier. you'll want to be able to go in and say, I know there's something, or even upgrade memory or any physical change. I know there's something I have to physically do at this box. I want to make sure that when somebody takes the cover off, the box doesn't go up in a puff of smoke and say, I'm dead. However, perhaps if that guy is not the guy that was authorized, if that authorization didn't take place, maybe that's what your policy is, that that device essentially destroys itself and won't boot again. And that's easy to do with fuses. So fuse-based policies are often some of the most effective. Once you blow the fuse, it's done, it's over with. But some fuses are programmable and have to be programmable, like the debug policy as well. And the last point is this becomes most important near the edge. So apparently I raced through this faster than I usually do. So this is the picture we started with. You've got a system down at the bottom with hardware that supports some number of cores, a hardware root of trust. You've got IOMMU and MMU, and that's important to protect both IO and the processor memory address spaces. You've got some number of SoC devices. You've got data in motion on a NIC or the equivalent. You've got data at rest on a disk. Both of those have to be encrypted. When the system is powered on, that hardware root of trust will verify firmware, option ROMs, platform, NVRAM, et cetera. Then transfer control typically to what's often called boot 0, which is firmware implemented on the platform. It verifies that firmware. The firmware there then in turn transfers control to some software bootloader, which it verifies. Software bootloader then boots, say, a hypervisor, verifies it first. Now you've got a static root of trust established. From there on, you implement VMs. And these VMs can be either trusted or non-trusted. You can mix them freely because they're protected from one another. If they're trusted, then you've extended the chain of trust. If they're untrusted, you don't care, but they're sandboxed. So to look from the top, talking about network security, you need management orchestration, software upgrade, and workload migration, all protected by AAA and remote attestation. Secure network protocols and configuration, VLANs we talked about, VPN, IPsec, et cetera. Line rate encryption for all traffic. From a hypervisor point of view, OS, applications, dynamic root of trust, you have to be able to extend the root of trust up into the VM and beyond. Now there's a problem there in current virtualized systems in that if you're using an Intel solution, for example, the access to the trusted device is not virtualized. So you cannot access functionality to store secrets, keys, measurement from inside a VM. Even though the operating system, Linux, for example, supports it, there's no access because the access to that device is owned by in this case, the hypervisor, and there's no virtual sharing. So that could apply to any implementation of security on a processor. It's not unique to any particular vendor, and in fact, all vendors currently have this problem. So extending that root of trust up and into applications beyond, the hypervisor can validate, but beyond that, you can't use secure keys, you can't store secrets, you can't use store measurements. There's a lot of things you can't do that you need to do to establish that chain of trust. Hardware, firmware, bootloader, static root of trust. We talked about that. So there's the typical mechanisms you see across the vendors, either a security processor, a TPM, or a TrustZone. And what I was talking about earlier was a virtualization in any of those. So that would be a virtual TrustZone, a VTPM, a virtual security processor, so that those calls into that hardware device would be virtualized, would be trapped by the hypervisor, would then be validated and could use the physical device. Now, the reason that's plausible is because these are not things you do often. So performance is not really a consideration. They're things you don't do very often, and you don't, for the most part, care how long they take. If it takes days, obviously you care, but minutes is not, or tens of seconds is not going to be an issue, and it's always going to be less than that. So trusted boot, measured or verified. There are different mechanisms to implement trusted boot. Different vendors support one or the other or both. It's not clear which one is better. Measured is, what measured is essentially a measurement that's done of the static code, static data, and parameters and some other information. It's stored in a place you can safely store secrets, and then when you instantiate this piece of code, like for instance, it could be the hypervisor, although that's pretty big. When you instantiate the piece of code, you do the same calculation with the same key and compare the results. If the results compare, then this is valid. It's a little more intensive than just simply taking a hash and checking the hash. Runtime integrity checking we talked about. Enabling hardware-based fine-grained TCBs, and I think you'll see a lot more of this in the future from processor vendors, because that definitely needs hardware support in order to enable it in a reasonable fashion and in a trusted fashion. Tamper resistance, we talked about sensor-based and policy-based action on detection. Policies need to be stored in fuses or platform-protected storage, like where you store secrets. They can't be accessible to anybody, and they can't be changed on a whim, obviously. Reset secrets on detect is very important. They shouldn't be able to be read out should somebody be have already tampered with the platform in some manner. And voltage and frequency monitors, we talked about that. So, I've got a lot of time for questions. Hopefully you haven't got that many. And I forgot to mention, and I hope I accomplished this, though that picture shows the Golden Gate completely encased in fog, or almost completely, this was not intended to be a presentation about security by obscurity. So, questions?
First of all, a round of applause. This is Paul Beneer, by the way. Paul, you want to grab no, you don't want to help me. You want to grab the mic, and just in case we got other people who want to ask questions. She is our editor for what used to be called the M2M Evolution magazine and is now the IoT Evolution magazine. What a name change, go figure. And if you guys have something you want us to write about, please feel free to connect up with us.
Okay, so I guess one thing that is clear from your presentation that security is not an amateur game. You really have to be an expert at all of this stuff. So the question is to really accelerate this whole industry, are there any products or anybody who is working on just encapsulating all of this stuff into like a Linux, a secure Linux, or some virtualization software with the operating system, so people can just buy that as a product and be sure that all of these things are already taken care of, rather than having individual companies worry about each of these details.
So in the cases where somebody mentioned I should do this, and I should have done this as I went through, and I didn't, I apologize. Most of this stuff, especially where there's a hardware functionality available from a processor vendor, they've provided the changes into Linux. Dare you want to run Windows? Windows has certainly put the changes into their code. So the hardware vendors work on enabling all the hypervisor vendors, all the OS vendors, and making sure that they have support for any of their hardware devices in the software. Things like like introspection using a software product, we actually experimented with one. It's not out in the market, and it was unfortunately incomplete in terms of hypervisor support. So it only ran on one hypervisor, which didn't make it viable. But it is possible. Somebody just needs to see that market, be convinced they can make money at it, and provide that. Or companies like us need to put people on it to do it for our products. But there are some things missing, but all of the things that are associated with processor, vendor, hardware are certainly supported in Linux, because they have, obviously the vendors have access to the hardware long before they all have big software development teams. And they all put that in and then upstream it. So it's in all the distributions at some point. But there are some things missing. And I'm sorry I didn't go through that when I presented.
Good work, Don.
Thank you, Bobby.
Sorry, I missed part of your talk.
Yeah,
In
I
fact,
noticed that.
I knew you would notice that. That's why I came back for you. But in case you already talked about this, no problem. But apologies. But the perspective I wanted to bring is the very special architectural position of fog computing or these resources, which, as you well say, need to be trusted, secured, and so on. With respect to what's going on below, the cheap sensors. Now we're talking about thin film with 2,000 gates on, spread all over the place. You cannot ask to those devices to have trust and all the heavy encryption and so forth. So I'd like you to comment on this role that fog can take to protect, to secure some of the infrastructure, the rest of the infrastructure, or proxy for these little smaller children underneath.
So I should have commented on that. I didn't actually. Thank you for bringing it up. So from a security perspective, it's problematic if anybody from one end to the other isn't fully secure, because you can tap in at that point and do anything you want with the data. Either fake it on the way up, fake it on the way down, stream it off so you can do something with it later. You can do anything with data in the clear. And so if sensors and smaller devices are not capable of providing the correct secure mechanisms, then you're just going to have to deal with the fact you're vulnerable at that point. However, once it goes up through a gateway, the gateway can present it, and whether the gateway's a virtual function in the platform or whether the gateway is a standalone device, it can protect it from that point up all the way to the cloud or wherever it's going.
Or it could be protecting the communication towards these devices, making it itself a proxy for it or a protector, a big brother.
So yeah, whatever goes up comes down through the same path. And so, but at any point so if the device isn't capable of encryption and decryption, then obviously you have to decrypt it at the point you're sending it down the device, and the data's in the clear and vulnerable. But as we get, in some cases, I mean, everything, the higher end becomes the lower end. Eventually, the economies of scale start to work for us, and those things are going to be more plausible as we get products in the space, and as people realize the vulnerabilities and the cost of that vulnerability.
Tim?
Yeah, Don,
Yes.
great overview and great summary of a lot of the technologies that are available here. I was wondering what aspects of physical security packaging and so forth to block against, say, EMF radiation or other tampering that you've looked into that also might augment this technology?
So you're right, there's a whole bunch, and I haven't personally looked really deeply into them. The biggest issue is cost versus threat, and how much it costs you to produce that box or those number of boxes versus the threat that may defeat your security mechanisms. But certainly sensors placed on boards and on the chassis, I think, are a minimum. And as you point out, there are so many other attacks that are possible, including freezing the chip before it shuts down so you can read out the data. I'm not sure how many people are going to, what kind of data is going to necessarily require that amount of protection. I think it'll be fairly small, but where it's required, it needs to be implemented.
If you're the NSA, you may go to very extraordinary measures to protect the physical vulnerabilities of your device.
Yeah, because you know who can break in.
That's exactly. Right. Any of that kind of stuff. You know, the avionics and helicopters routinely self-destruct if the helicopter crashes.
Yep.
The FPGA is wiped, and all I have is a bunch of transistors with no logic discernible. I think that 80–90% of the fog nodes are going to feel a little bit like traffic signal cabinets. So if you're pushing the walk button, you see that yellow cabinet sitting on the street corner. It's got a pretty good lock on it, and there's probably a door open switch and a tamper alarm, and there might be, you know, an optical sensor to see if somebody's doing something. There might be a tilt switch like in a pinball machine to see if the thing gets knocked over. Those are the kinds of sensors we're talking about. I think a lot of our stuff doesn't have to go to military-style extraordinary.
Although where we deal with military, it will.
I'm going to argue that later, but go ahead, ask your question.
Yeah, back to the question that this gentleman over here asked before. Aren't there protocols being developed for basically things, sensors that are, you know, compressed IPv6 and things like this?
Yeah, but that doesn't help. It's still clear in the clear.
I thought that there were security protocols going along with those. DTLS, that's not a.
Hold on. Here's the problem is we're recording and we're not hearing you.
So this is one of my favorite things. A secure key today is about 2K, right? That's what you send to 2048. That's how much memory these things have, right? So all your RAM is, they have less than that. All your RAM is to store your key, right? So I think, as an industry, we have to assume that the sensors will be hacked, right?
Yeah.
You have to assume that they are vulnerable, and then you have to mitigate upstream.
Yeah, I mean, their whole mode of operation is, I turn on, do something for a while, go back to sleep. Turn on, do something, go back to sleep, but I sleep a lot more than I'm awake, and there's virtually no power, no capability, very little capability built into that thing because it costs 2 cents.
Great presentation, Don.
Thank you.
One thing to follow what Carlos said, we will have a trillion plus devices. Okay, plus minus, I don't care. But the question is, I think we need to do security because what happened is that people will tempt, I mean, you will break in. There's no way you can protect. This will not scale to the number we have.
Yes.
We have to look security in a different way. Because if we keep doing security the way we're doing, the thing will break. We will not get there. So this is great, but this is more of the same. I think that
Well, it is a collection of current technologies that are available to solve the problem.
So my question to you then, what do you envision the next few years, because this thing will not scale?
Well, part of the answer to that question I can't say, because I know some solutions that are coming via RSNDA from vendors. So I know some things that are coming, but I think things that supersede a lot of these approaches and make them simpler, but are still hardware-based, is the kind of thing we're going to see, and they're going to be embedded in the processors and devices. I know that's probably not satisfactory, but to get specific, I'd have to violate.
I would like to add a little bit to that. And I built up on what something I mentioned this morning. I strongly believe that in many situations we are going to have these sensors and actuators working with the look of a system. They are clustered in certain ways, but with more specific functionalities that we have, say, in a laptop. So if we pay attention to what those functionalities are, the universe of interactions with the external world are more limited. And that gives an opportunity for a gateway or whatever the next node they communicate to enforce certain policies that will very more rapidly detect misbehavior. So I think that I have been talking about this for a while. I haven't really worked on that. I have been sharing with people. But I strongly believe that that's a very rich area to look into. Of course, I mean, this morning I made the joke about this refrigerator being a spammer. And my response to that, well, the way to control that is to think of the home as a certain environment in which you articulate very well who the refrigerator will talk to and doing what. But in a more serious context, I mean, you have things like people are very concerned and because they have things in medical devices like insulin pumps. They have been proven to be vulnerable to tampering externally, right? And so they can inject a doses that is lethal. Well, the answer to that is probably in that case, I mean, you have, again, a certain limited number of functionalities, and probably you will have to do a little more expensive devices, probably with some memory of what was injected in the last 24 hours or whatever, and do policies around that. So I'm saying, and all goes to what at the very beginning, I mean, don't mention, which is the cost, security and cost, and the risk. What is the risk? What if something fails? What can go wrong?
And I think those are there are two different things at work there. There's detection and prevention. Some things you can prevent. Some things it's either extremely difficult or impossible to prevent, but then you have to detect. And those are, so I think the ideal is to be able to prevent almost anything, but it gets way too costly at certain points. So then you inject something that's less costly that detects and ameliorates as well as it can what happened. But I think many of the most important methodologies will be, and in the future, will be in the realm of prevention as opposed to detection and reacting to the fact that something has happened.
Couple comments. I think I hear you agreeing with this, and I agree with you as well. The cost-benefit analysis of implementation of security, to me, says that the vast majority of sensors, which are intended to be very low cost, simply you have to assume that they're vulnerable. You're not going to be able to implement security practices at that level. There are companies that are looking at 10, 25, 50 cent type of sensors, which all they have is an IPv6 stack, a D2A, an A to D, multiplexers, and pins. That's all they want to do because they want to be able to proliferate this everywhere at low power, battery operated. That's a big deal. So you have to assume that that's where your vulnerability is and put best practices above that. I kind of think detection to make sure that your content is valid is going to be important, but if you can prevent it in the first place, which is my second point, we're treating security in the IoT space as an afterthought, and that's a problem. If we get to scale without having implemented security as a design part of the application you're deploying, we're in deep doo-doo. Sorry, French, pardon my French there.
Absolutely.
For doo-doo? Man. Don, first of all, you've proven me wrong. So this was a fantastic security talk, so kudos on that.
Well, thank you.
But secondly, as you were talking, I basically thought of the CISSP exams, and I basically decided that I was going to have to learn about some sort of sensor or detection at every single layer, because in theory, I could basically secure my security on top of my security on top of my security as I went through the layers. Does this make any sense, or was I delusional as you were talking?
So in terms of detection, that might make sense. In terms of prevention, I'm not sure that makes sense.
Okay, fair enough. Now, just out of curiosity, is it possible that there's ever a situation where an internal person is going to be the bigger threat than external internet?
Well, yeah, I mean, that was one of the things about an authorized person getting access to debug. If you're inside, you may be able to arrange that. An authorized person can, because you have to do maintenance, because you have to allow certain people to do certain things. That's a problem with military, right? Exactly the same.
If you're an elevator technician, you can kill people because you've got the keys that open up the door
Right.
of the house, right? Same problem in the quantum computing world. If you're trustworthy and vetted, drug tested, and all the other things that might be necessary to actually have the cryptographic keys to go in and twiddle with the configurations and software on fog nodes, you're taking a serious responsibility, and your boss better trust you, and you better have the systems and training necessary to be worthy of that trust.
Well,
No sensors.
that's the biggest issue was, as we were saying, what level of security. And I came away saying electricity and electrical's got to be hardened as much as possible. And, in case you haven't noticed, that's not their forte, I mean, 45-year life cycles on things is not exactly what we'd call up to date. Any commentary there?
Well, I think 45-year life cycle is going to become, any life cycle over 5 or 6 years is going to become almost non-existent for any device, and that's probably going to decrease over time. I mean, my son's getting a new phone every 6 months. I think we're going to look at a lot more disposable and replaceable, because technology will move so fast and entice us into wanting that new thing.
Yeah, but M2M and IoT devices last for a long time.
So far
and
they
that's
do.
part
I
of the issue.
wonder whether that's going to continue to be the case.
Exactly.
Type 500 telephones with 90-volt ringers last a long time too, but you don't use them anymore. I think we're going to replace fog nodes about every 4 Moore's law cycles. Round numbers. I just think that's kind of what we have to pay for as a factor of 16 performance. After that, it's worth it because the next generation of applications and performance demands are going to justify the truck rolls and all the things necessary to update that hardware.
Okay. With that,
We're done.
please give Don a round of applause.